Joystick Positioning Visualizer, or more formally known as Two-Dimensional Twain, task without an interesting name, is a project that emulates the positioning of a joystick on an 8x8 matrix and serves as an extended challenge from the 1D Twain, which instead uses the Moreland bar graph and a potentiometer. In place of the typical Arduino development boards like the Uno or Nano is the Dolgan development board, pioneered by former ace Josh Dolgan. It's centered around the 8 MHz AT-Tiny84 instead of the standard 16 MHz AT-Mega328P and is housed in a custom 3D printed case. The current DDB version 7 features female headers for shields and breadboarding, ISP programming through a 2x3 header, and some SMT components such as an onboard LED and a 5-volt regulator, allowing power through the battery jack, USB, terminal blocks, and SparkFun Pocket Programmer. It also offers serial support by connecting a USB to serial converter to the broken out TX and RX pins. This project can be broken down into input, processing, and output sections, tied together by the DDB V7 and its shield. Like the Arduino Uno shields, the DDB V7 shields allow a user to simply place one on that caters to their specific needs. For this project, a universal shield provides wiring flexibility for appliances using breadboard wires, connecting the Matrix Made Easy appliance and the joystick to the DDB V7. As you guessed already, the input originates from the joystick, which is simply made out of two potentiometers, each measuring the horizontal and vertical position. Therefore, it outputs two analog values and takes in power and ground. There is a fifth pin which provides the output from a button, activating when pressing down on the joystick, but it is not used in the project. The AT-Tiny84 reads these analog values with its ADC converters on pins 4 and 5 and outputs a dot with a column and row value on the Matrix Made Easy corresponding to the readings. The Matrix Made Easy, designed by former ace Hugo Reed, essentially extends the Moreland bar graph to a 2D matrix by adding on a daisy-chained TPIC6C595 shift register designed to sync current. Therefore, the 74HC595 output controls the column LEDs and the TPIC6C595 syncs current from the LED rows. One 16-bit shiftout is enough to provide the column and row bit to turn on a single LED. All of this constitutes the output section of the project. AVR assembly language, instead of the regular Arduino C code programmed onto the AT-Tiny84, is the processing section that ties the input and output together. Assembly is one of the most efficient and lowest level languages you can code in, and is simply binary machine code assigned names for ease of understanding. The syntax is made up of certain instructions in an instruction set that the MCU stores in Flash as machine code, with corresponding variables or constants attached. There are a wide range of assembly languages for programming different processors, such as AVR assembly used to program AVR MCUs, but they all follow the same basic format. These instructions are executed with an incrementing program counter located at the program memory address of the instruction being executed, with each instruction taking at least one clock cycle. You may notice that what I'm describing here is essentially a more complex version of the 4-bit chump computer, using 8-bit instructions instead of 4, which I find pretty cool. Anyway, here's the code sketch written in AVR assembly using the Microchip Studio IDE, a much more advanced IDE than the popular Arduino version. When going through the code, I won't go through every instruction as it will take too long and instead give you the main gist of it, where you can pause the video to take a look at the commented code or a PDF of the AVR instruction set linked down below. So first we have some defines and equates, assigning variables, ports, and registers custom names for clarity. The next part is the interrupt vector table, specifically the reset vector that is right at the beginning of Flash, taking priority over any other interrupts. Once a reset occurs, the code will jump to the setup label, which is again just an address in Flash, marking where the code begins. Port A pins are set up for output and the loop section begins. PA4 is set for an ADC read and the function to do so is called, where the program memory jumps to the beginning of it. Here, ADC is set up through altering the respective registers and waits until a 10-bit ADC value is available. With this value now in ADCH and ADCL, it is shifted so that the upper byte is in ADCH. Shifting this value 5 times to the right converts it into a 3-bit value, where it denotes the number of shifts to do to get to the column dot position. It is then shifted out to the 595. The same thing repeats for the vertical axis, shifting out the row dot position. The shift register values are finally latched to their output pins, displaying the dot and the loop repeats, completing the transition from the joystick to the matrix and cementing a new software milestone in learning assembly.